turntable of radius r1 is turned by a circular rubber roller of radius r2 in contact with it at the outer edge. So it's something like there's something like that, and there's something like that, and one turns the other, and they want the ratio of their angular velocities, omega 1, omega 2. I mean, physics, I like physics, but I have no idea how this problem, like, I don't really know why this is an interesting problem in physics. So I'm just going to look up the solution and see if we can
Figure it out.
figure it out. Okay, so I found the problem here. Okay, so it's pretty straightforward actually. The one has omega 1 r1, and the other one is omega, or the velocity of v1 is omega 1 r1. Velocity 2 is omega 2 r2, and because they're turning, their velocities are the same.
Hmm.
So since they're the same, you set them equal. Omega 1 r1 equals omega 2 r2,
Okay.
and you solve for that ratio, omega 1 over omega 2, and you end up getting r2 over r1, r2 over r1.
Oh, that's just the whole thing.
Yep.
I have to use a subscript for this. All right, let's see. This thing is so weird. I don't know why it's not letting me. Oh, there we go. Okay, that's what I meant. And divided by R2. What? This is incorrect. Oh, wait, no, wrong way. R2 over R1.
Yeah.
I did that incorrectly. My bad. There we go. All right. Here we go. The tires of a car make 74 revolutions.
All right. So I see the front tires question here.
Yes.
Okay. Okay. Let me snip this one in, and at least part A. The tires. Oh, this is actually, maybe I can just get to that question here. 22. Maybe it's in the. Yeah. Okay. The tires of a car make 74 revolutions as the car reduces its speed uniformly from 94 kilometers to 56 kilometers per hour. So we can find. What are we trying to find here? We're trying to find the angular acceleration. Angular acceleration. Okay. So the angular acceleration. of the tires. Okay. Wow, there's a lot that goes into this. Okay, so the thing that we're trying to find here is we have this equation omega final squared equals omega initial squared plus 2 alpha theta, and we're trying to find alpha. So alpha is the angular acceleration. That's omega final squared minus omega initial squared over 2 theta. So okay, great, Matthew. Like, what does that mean? Well, it means we got to find we got to find a bunch of these things. So um, we can start with uh, omega. So omega initial is v initial over r. So the initial velocity is 94. Is that okay? Hopefully you're there.
Yes.
So it's 94, but it's in the wrong units, in kilometers per hour. So we have to convert. There is in 1 hour there are 3,600 seconds, and in 1 kilometer there are 1,000 meters. So that's the first thing to do.
Oh, convert. Okay.
Convert that, but then you divide whatever you get for that number. The radius is 0.84 divided by 2. So let's
Okay.
make
There
sure
you
we're
go.
on the same page with that number.
Now, is that 180 over 1 kilometer over there?
It's 3,600 seconds, and there's 1,000 meters and one
Oh, 1,000.
kilometer.
Okay, so I multiply 1,000 by 94, divide by 3,600. I get that number, 26.11111 whatever. And then divide that by 0.84, which is also divided by 2. And so I get 62.16. What do you get?
You said
62.16.
yeah, 94 times 1,000 divided by 3,600 and then divided by 0.42. Yeah, 63.5 is what I got. Okay, so that is the first one. That's omega initial. Now we got to do omega final. So omega final is the same thing. It's the v0 or v final in this case over r. So it's the 56. So it's times 1,000 over 3,600 divided by the
Okay.
0.84 over 2.
56 times 1,000, you get that 56,000. Then divide that by 3,600. You get 15.5 Repperton bar, and then you divide that by 0.84 divided by 2. 37.037.
Okay,
That's what I get.
give me that one more time. 30.
37.037.
So 37 ish, we'll say. And then to find the angle, so the angle we can find by the number of revolutions. So it's 74. It's 74 revolutions times 2 pi radians.
Okay.
So we'll get that number there.
So 4 times 2 pi radians. 474.95557. What'd you get?
Go ahead and give me that number again.
464.9557.
Yeah, that sounds good. So now we go back to our equation. Our equation for alpha is omega final squared, which is this 37 squared minus 63.5 squared. That's this one up here, divided by, and then you have to put that in parentheses, divided by 2 times 464.96. It won't be very big. It'll be a negative number. I mean, it'll be around, I don't know, it'll be around 3 or 4, 2, 3 or 4, somewhere in there. It's not super big.
Okay, so I did that wrong. Definitely.
Make sure this is in parentheses too.
That must be a bit of a problem. 37 squared minus 63.5 squared, parentheses, divided by parentheses, 2 times 4.6. No, 464. 464.96, parentheses, negative 2.8.
Okay, so that's totally reasonable. Radians per second squared. All that work for such a small number. And then there's part B and C. Okay. Oh,
Those are incorrect somehow.
no way. Did you put the negative in?
For angular acceleration,
Yeah.
I had negative 0.29, and then I put negative
Oh,
0.28.
0.29. Oh, it should be much. No, no, no. I mean, it's
Re-
got to be.
Review your calculations and round to two significant figures in the last step. 8.6? I put 8.6 in there. It still doesn't put it in there.
Yeah, it's minus 2.9. Um,
2.9. Oh, wait, just positive or negative?
Negative.
Still marks as incorrect for some reason.
Well, okay. I wasn't checking your these numbers are all different from but they were close enough. So, well, 74 times 2 times pi, 464.96. That's reasonable. 56 divided by 3.6 divided by 0.42. 37. That number's fine. I don't know. Boy. And then 94. 94.
What a pain this thing is designed in.
The first number's a little bit off. It's 62.7.
62.7? Oh.
It wouldn't be it might be enough because you're squaring it to get something. Yeah, so this one ends up being minus 2.8. I mean, I thought you tried that already.
Yeah, I did, but it didn't work for some reason.
Well, the other answers depend on part A, so that makes it tough for us.
I could just request the answer and just take it. I'll just request it, whatever. You get negative 2.68. What? How'd that happen?
Um, I mean, maybe some rounding. Who knows?
That's very odd.
What do you want to do? Do you want should we go on to part B with that answer?
Yeah, let's go
Okay. So give me the value, the alpha here. It's minus 2.68.
on. Yes.
Okay. And that is key. So in the next problem here, next part of the problem, it says that T is equal to omega final minus omega initial over alpha. Your omega final is 0 because it slows down. Your initial is where it was at, which is this 37 that we just found.
Mhm.
And then you're
Yeah.
dividing it by minus 2.68. So 37 divided by 2.68.
All right. Say it one more time. 32.68.
37 divided by 2.68. That's
Oh, my bad.
we're
Let me
just
divide that again. My bad. 2.68. We get 13.8
okay. And that's positive. That's seconds.
seconds. Yes. Correct. Excuse me. All right. If the
Okay, part
car
C.
continues to accelerate this rate, how far will it go?
So then this is another, I'm condensing the formula here, but the change in the angle is omega final squared minus omega initial squared over 2 alpha. So again, because it goes down to zero, 0 squared minus 37 squared over 2 times minus 2.68. I'm just plugging numbers in that we got from the previous part.
All right. Put that one in there. 37 squared, 113 divided by 2 by 2.68. 1834.
Did you divide? Did you
I,
put that in
I,
parentheses?
I must have done that wrong. Yeah, 2.2.68. You get that 5. Yeah, that is definitely wrong. All right. 255.41.
Okay, 255.41. Great. That is not the answer. The answer is the change in position, which comes from the radius times that number you just found. So your radius, if you go back, is 0.84 divided by 2 times that number.
Sounds good.
And should be, around 100-ish, right in there.
I get 107.27.
Okay, that sounds reasonable.
What's the unit here?
It's meters.
Meters. All right. Incorrect. What? Did I do this wrong again? Let me see.
Oh, you know what?
255.41.
There's a bit more. There's a bit more. Um, there's a bit more. Okay, and then it's this plus the 74 revolutions. Oh my gosh, there's so much to this part. Okay, so, so it's the number you just got plus. So it's this number you just got plus you went your radius times the 74 revolutions. So it's the radius times delta theta again. So you're going to add this to 0.84 over 2. That's your radius again. And then you went 75 revolutions times 2 pi, because it's 2 pi revolutions per radian.
Oh, so 2 pi radian because it's what? Say that one more time.
It's 75 revolutions times 2 pi radians per revolution.
Oh,
So this is R. 80.84 over 2 is your R, and then your theta is that, 74 revolutions. I grabbed the wrong number there.
oh, 74 times 2 pi. You get that 474. All right, then you multiply that by 0.42. I get 195.28. 195.28. Now let's see if this works. Incorrect. What?
So you have to add those two numbers together. So it should be around 290-ish
Wait, so add 195.28 to what?
to this number you found in the previous part.
Oh, in the previous part. Okay.
This right here, that number.
Plus, all right. Check that other one. What was the other one I got? 302.55.
Okay. So 302.
Perfect. All right. That was kind of painful. All right. On to the next one. The moments of inertia and rotational kinetic energy.
Is it part of the email that you sent, or is it a new email?
It's still in there. I
Okay.
sent a new
You
one.
sent a bunch of them. Is it this electric ceiling fan?
Hmm.
Okay. Wow, we got a lot. Must be a lot more of this. All right. Wow. So this one doesn't come with a problem number. Huh. Okay. Um, oh wow. 1.192 seconds. Okay, so the zero point 0.3 revolutions. This is not a good reference.
All right.
Um, okay. All right. So I think I've got enough here that we can start to do this. Let me grab
Awesome.
the snip the question. Electric ceiling fan. All right, electric ceiling fan is rotating about a fixed axis. It has an angular velocity that's omega of zero point 0.3 revolutions per second, and then alpha is the 0.913. They're directed counterclockwise. I don't care about that. And they have a diameter of so the radius is 0.73 divided by 2, which is 0.6365.
Mm-hmm.
So the part A asks for the angular velocity 0.192 seconds later. So the angular velocity omega final is equal to omega initial plus alpha times t plus
All right.
alpha time. Sorry, it's not alpha times t. So we have that. We have it's 0.3
Yeah.
plus 0.913 times. I'm just trying to get the number here. 0.192.
Awesome. I get 0.475. What do you get?
Yeah, that looks good.
Is that for
That's for part A.
okay?
Give that a try. The units are revolutions per second. Yeah, that's right.
Correct. Important if you use this answer in layer parts, use the full unrounded value in your calculations. Okay.
The number of revolutions is in that amount of time is so the it's this theta. It's like theta equals theta 0 plus omega t plus 1/2 alpha t squared. In your case, it wasn't rotating, so that's why it's 0, and that's 0, at least according to this thing I'm reading. So your alpha is 0.913, 0.913, and your t is the same t we used in the previous problem, 0.192 squared. So it's just this part here. And then you have to convert that to, wait, how many revolutions? Yeah, so you have to convert that number.
1, 3. All right, and 0.016.
How many revolutions?
And then do I add that to my older one, to the 0.475?
No, it's just that. It's just that 0. Whatever number you just got then is the part B answer according to this thing that I'm looking at.
That's quite this. What? It says no. It says it's incorrect.
Okay, well, let's see here.
Wait, when I make that calculation in the 1/2, 0.913, multiply all that, do I add it to anything?
No,
No?
no. It's, I mean, according to this solution, which, I mean, these are all just somebody's who knows physics better than me trying to do this. So let's try part B. Well, it does have this component. It does have a 0.3 times 0.192. That, I mean, that does seem reasonable.
Oh, wait. Here we go.
Yeah.
Zero
Give this,
point-
you do want to add this to it.
Oh, that's what I was missing. Oh, there we go. 0.0744. Correct. There we go. All right, on the C.
All right, so part C, C says, what is the tangential speed? So VT. We're trying to find VT, and VT is, I don't like their notation. I don't understand it. Their VT is
Excuse me.
is omega R. Omega R. Okay. Okay, so their part C, there you say V tangential equals omega times R. The omega is 0.486. Where did that come from? Okay, so that answer from part A, what was the answer for part A?
For part A, I got 0.475, and I can list off the extra numbers.
Okay, so it's that number times the radius. I'm sorry, times 2 pi.
Times 2 pi? Okay.
Times 2 pi. That becomes omega. And then your radius is the times 0.365 here.
0.365. Okay. 1.09.
Yeah, that's super reasonable.
Correct. All right.
Okay,
on
great.
the D.
Part D is the acceleration tangential. Okay, so the acceleration tangential is, or is it asking for acceleration?
This one?
Yeah.
This one is asking for
acceleration.
Yeah, acceleration.
So acceleration is two things. Acceleration is the square root of the radial acceleration squared plus the acceleration tangential squared. So you have to find two things. So the acceleration tangential is omega squared r. So it's this number you just got up here, this 0.475 times 2 pi, but you have to square that times the 0.365. That's this one.
Oh, I see. Okay. All right, I'm gonna fix that up. 0 point whatever that number is.
Yeah. Okay. And then they we the acceleration, I'm sorry, this is the acceleration radial. The acceleration tangential is alpha times r. And we found alpha in, I think we found alpha. I guess we didn't find alpha yet. So alpha is given. I forgot that it was given. Alpha is 0.913 times 0.365. So you get two numbers here. Both of these numbers go into this square root thing, and you square them. You get your number here, and you square it. You get your number here, and you square it, and then you take a square root of that.
Awesome. All right, so I'm calculating that 0.913 times 0.65 plus that the one up top, or can you explain it one more time?
You have to get these two numbers. Did you get those two numbers?
I'm getting them right now.
Okay, so when you get those two numbers, you square the first number, then you add the second number you calculate and square it, and then take a square root of all that.
All right, so the second one is 0.333245.
That doesn't seem big enough. Let me check that again.
0.913 times 0.365. Same number. That number times.
Oh, you have to multiply this number by 2 pi.
Oh, that number by 2 pi? Okay, yeah.
Yeah, so because it's not big enough, I just see that here.
0.913 times 2 pi times 0.365. And I get 2.09 for that one, for second one. And this next one, 0.365. Wait, no, I should hold off. 0.475. Whatever. Let me get that in there. Dun, dun, dun. And then times 2 pi. So that number, square that up, times 0.365. 3.255.
Okay, give it a try. I mean, there's so many calculations here that it, it's rub of the problem here, that if you get it or not. We can. Oh, is there more?
Yeah, there's more to this.
More. Oh, not to this problem. Or is there to this problem? I hope not. We should go back to like 8.14 because these will be more clear.
Squaring it up, and I get 3.87. What? It says it's wrong. 3.87.
I suggest we move on. I mean, you're not far off for, because it's around 4. I have no idea, but it's right around that, and uh, there's just too many. We can get another problem or two done if we move back to something.
Yeah, we can move to something else. Let's go.
So 8.14 is the next one that I pulled up here that I think would be good to look at. The nice thing about these is I can match them up to the book, to guide you through the solution, because without that, I don't know how you. I mean, it's tough to do. So um, here you're trying to find the angular acceleration. The angular acceleration is omega final minus omega initial over t. Whenever you're given time, use an equation like this. So they give you they give you an initial speed here.
Mm-hmm.
sorry, just getting caught up here. From 120 to 3. Yeah. So at 120, I'm sorry, 150. I'm reading the wrong number. 150 times 2 pi over 60 gets you to radians per second.
Sounds good.
And that's your omega initial. Then you do the same thing for 320. You get your 320 times your 2 pi over 60.
All right. Which one do you want me to calculate? Both?
Yeah, go ahead and give those both to me.
All right, first one's 15.7. Next one is 33.5 for the second one.
Okay, so take the number you got for the second one. I think you said 33.5 minus the one you got for the first one. I think I heard 15.7 or somewhere in there, over 3.7. Make sure you put this in parentheses up top, and that is your alpha.
4.81.
Yeah, that's pretty reasonable.
So it's correct on the B.
Okay, part B. Part B is finding, what is part B? Finding the radial component of linear acceleration. Okay. Okay, so they want you to find in part B AR. AR is R times omega squared. We've got the radius, okay, but we don't have W, or do we? Nope. So W final is equal to W initial plus alpha times T. So we have this initial omega. It's from the first part of the problem here. It's the 15.7 that you just got. You'll want to use the unrounded form of that plus the alpha value that you just calculated, whatever you used in part A. Give me that number again.
So 15.7 plus 33.5
Is no. The answer to
overall
part A.
number 4.
Yeah.
4.81.
Okay, 4.81 times the time that they give you, which is 1.2.
Divided by 1.2 or multiply. Okay.
Multiply. So that number, whatever number you get out of here, so, and this is where we ran into problems last time. You can't use the rounded form of any of these. You have to use the previous values. That number you're squaring and then you're multiplying by the radius.
So I square up that the W squared, right?
Whatever you get for this over here on the right.
21.42.
You square it, and then your radius is 0.72 divided by 2, so 0.36.
1659.
Big. What did you get over here for this?
For the one on the right?
Yeah.
Oh, I got what is it? 21.42 for the right.
And then did you square it and then multiply by 0.36?
Squared it times times 3.6.
And you got
1659.74
okay. I mean, we're way off on that. It like the number, the 21 sounds right. 21 squared times 0.36 is 158, more or less, right in there, 159.
Yeah.
I heard something totally different. So like it's around that number. It's got to be around this.
$159 meters per second squared.
Yes. Well, roughly. I mean, I'm again. So I'm trying. If I jump into all the calculations, I mean, you. This is the key part of this is doing this for WebAssign or
Mhm.
Pearson here. Um, 15.7 plus the 4.81 times the 1.2, and then you square that number. That's whatever that is, but then you multiply it times 0.36, and it's actually 166 is what I got when I do this calculation out.
166. Okay. Review your calculations and make sure you round to two sig figs in the last step.
Yeah. So again, you got a rounded value here, a rounded value here. You got to make sure those are totally perfect.
Wait, no, 4.8 is where we ran into problems. It's supposed to be 4.8 from what I got, not 4.81. So I guess it's giving us problems.
Okay. Let me jump in here. I'm gonna have to go back and um, you have to store value. So like omega final is 150 times 2 times pi over 60. So that's whatever 15.7 ish. Or that's omega zero.
Yeah.
Omega final is 320 times that. So it's 33.5, but a bunch of decimal places. You got to keep those numbers. So like you have to be really good about going like second ANS or going out 4 or 5 decimal places. So then your alpha, your alpha here is omega final minus omega initial over time, which is 3.7. 3.7. Okay. So that's 4.8111448, bunch of decimal places. All right. Now for this one, this new W that you need, this new W is the omega initial plus the alpha value times 1.2. So we get 21.48, so on, so on, so on. So we take that number, W, so we take 0.36 times that W squared, and the answer is 166.12. So it said to two significant figures because that could be 170.
170 is correct.
Okay.
On the C.
Let's see. Um, your instructor would give you full credit for this if this was a paper test. You're close enough, and that's what real physics is. Part C here, this A tangential is R times alpha. So your R we already have, it's the 0.72 divided by 2. Your alpha is from part A, that was the 4.811. So that is 0.36 times alpha, 1.73. How many significant figures does it say? 2. So 1.7
1.7. Where are the units?
meters per second squared.
Perfect, correct. All right, let's try to do these last two real fast.
Unlikely.
Yeah.
8.23. Okay. If you have a check account, you can follow the numbers, but it's very cumbersome. You have to really be very careful here. So small rubber wheel is used to mount. Yeah. Okay. So this one. All right. So this question here, 8.23. We got alpha equals that. I'm gonna cut through as much as I can. Alpha 2 equals R1 alpha 1 over R2.
Okay.
So let's just accept that as being true. When you are finding the ratios, you don't have to convert like the centimeters to centimeter to meters. So that's 2.8, that's 21, and then they give you that as 6.7 there. So there's a few things that go into getting that value, but go ahead and calculate that, please. And
Good morning.
those are all given, so we should be fine on that.
do 21, 0.89.
Okay, go ahead and try that, please.
Correct.
All right, so part B. Part B, you're trying to find time. Okay, so time, great time. You have this equation, omega final equals omega initial plus alpha times t, and that leads to t equals omega final minus omega initial over alpha.
All right.
Okay, what do we have? What do we have? What do we not have? So we have from here, we have 75 revolutions per minute. So that's 75 we're going to convert. So omega final is 75 times 2 pi over 60. So that number is going to go, so that goes over here in this W final.
7.53.
Yeah, W initial is 0, and then your alpha is what you calculated in the previous step up here.
So divide that by, what was it? 0.89?
Mm-hmm. It should be
8.47.
How much?
8.47. Dang, you're not correct.
Okay, so you gotta like the answer is around 10 seconds. I don't know. Maybe you got. Let me try. Let me see if I can get this real quick. So it's 75 times 2 times pi over 60 divided by that number you just found, 2.8 times 6.7 divided by 21. So I got 8.8. Is that what you just said?
I had 7.8.
Try 8.8.
But 8.8 is correct.
Okay. All right. That's all we've got for now. I would again, if you have a check account, you could probably get a lot of this done. But it is a little slow. So thanks, Jack. Thanks for scheduling. I'll look forward to helping you again next time.
Appreciate it.
See
Thank
you. Have
you.
a good night. Bye now.